Yeah, so I'm Zofia Stanley at the University of Colorado Boulder. I'm a graduate student there in the Applied Math department. And I first just wanted to start by thanking the organizers for having me here today, and also just for organizing a wonderful series. I've really enjoyed it so far. So today I'm going to talk about work I've done jointly with my advisors, Ian Grooms and Will Kleiber, on constructing multivariate localization functions, specifically for use in strongly coupled data assimilation schemes. So just to sort of orient ourselves, I want to talk about the background error covariance matrix in coupled data assimilation schemes. And so what we know about coupled data assimilation is that we can write this background error covariance matrix in a block form. And so here I'm showing the background error covariance matrix for two different components, X and Y, but you can think atmosphere and ocean if you prefer. And the diagonal blocks show store the covariances within a component, and the off-diagonal blocks store the covariances between components, or between fluids if you prefer. And so what we know about strongly coupled data assimilation is that these off-diagonal blocks are non-zero. And since we're specifically focused on strongly coupled data assimilation, we're going to be focused on how to treat the covariances in these off-diagonal blocks. And I am focused on localization today. Specifically, I'll be talking about Schur product localization and B-matrix localization, although much of what I'm going to talk about is extensible to other types of localization as well. And so just like we can write the B matrix in this block form, we can also write our localization matrix in the block form, and then we'll just take the element-wise product of the localization matrix L and the background error covariance matrix B. And so just like we were interested in these off-diagonal blocks in the B matrix, I'm going to be focusing on these off-diagonal blocks also in the localization matrix as well. And so I just want to take a moment to talk about what this localization matrix might look like. So because we're working with localization, obviously we're working with ensemble data assimilation schemes where there are spurious correlations, and we need to mitigate the impacts of these spurious correlations, specifically at large distances. And so our localization matrix L might look something like this, where we can see these very clear 4 blocks showing up here. And these diagonal matrices, diagonal blocks rather, that you can see might look kind of familiar to if you've seen localization matrices before. They have ones along the diagonal, and then some off-diagonal elements that are non-zero as well, and then the rest are 0. So they are sparse matrices. And here, these diagonal blocks would be the localization matrices that we would use to localize the within component covariances. And something we see a lot in coupled data assimilation is that the localization radius that we want to use can often vary widely between the different components. So for example, in the atmosphere, we might want to use a localization radius that's almost an order of magnitude larger than the localization radius we want to use in the ocean. And so this schematic is sort of showing that difference, where the width of the diagonal here and down here in this lower right block as well are showing sort of the localization radius. And so here we have one component with a much larger localization radius than the other component. And so I want to ask a very specific question, which is, if we have certain functions that we want to use to construct these diagonal blocks, what functions can we use to construct the off-diagonal blocks? And I'll break that question down a little bit. So basically, if we had sort of a weakly coupled scheme, right, where we knew which localization function we wanted to use, say, for the atmosphere, and which localization function we wanted to use for the ocean, is there a way that we can construct a localization function for the cross-domain assimilations, or can we construct a cross-localization function that still preserves lots of nice properties of localization matrices, and I'll get into that in a minute. But specifically, the functions that I'm going to be looking at here are the standard Gaspari-Cohn fifth order piecewise rational functions. So here you can see that I'm using the same function to construct both of the diagonal blocks. The only difference is that I'm using a different localization radius for each block. And so here, this localization radius is much larger than the localization radius I'm using for the lower right block. And so the question that I'm really asking to be more specific about this is, if we fix the within component localization functions to be the standard Gaspari-Cohn function that are widely used in data assimilation, then can we construct a cross-localization function such that this whole localization matrix that we've created now, this block, these 4 blocks all put together, such that this whole localization matrix is non-negative definite. We already know that Gaspari-Cohn leads to non-negative definite functions, so we already know that those 2 diagonal blocks will be non-negative definite, but what we're asking now is, can we make it so that this entire localization matrix is non-negative definite? And this is really important for variational schemes, so en var, for example. And then the other thing that we want, this is I guess a little less important, but the other thing that we want is the cross-localization blocks to be sparse. And so we know that the diagonal blocks are sparse because the Gaspari-Cohn function is compactly supported. And what we're asking is, can we make sure that the function that we're creating for the cross-localization is also compactly supported, so that those blocks are sparse and the entire matrix is sparse, which just aids in computation. And so to answer this question, I want to dig into how one of these diagonal blocks is created. So really what I want to take us back to is, how is this standard Gaspari-Cohn function created? So if we go back to their 1999 paper and take a look, we see that their localization function is created through a convolution of 2 different kernels. And these kernels are really quite simple. They're just tent functions. So you can see them down here, with the caveat that the convolution is performed over R3. And so these kernels live in R3. They're radially symmetric. But if you take one slice of them, they're basically tent functions. And so this kernel convolution ensures that the localization function that we create is both compactly supported and produces a non-negative definite function, a positive definite function. And so this is how these 2 localization functions that we're using to construct our diagonal blocks are created. So LXX is the convolution of KX with KX, and you can see this kernel KX over here. Again, it's just a tent function. And LYY is the convolution of KY with KY. Again, it's just a tent function. The only difference between these 2 kernels is the width. And so the localization function with the shorter localization radius has a kernel that's narrower, and the localization function with the longer localization radius has a kernel that's wider. The difference in height is just due to normalization. So we normalize it so that the value of both of these localization functions is 1 at distance 0. And so that's the only difference in height there. So then the question is, can we construct cross-localization functions, LXY and LYX, to be used in those off-diagonal blocks sort of in the same way? And I hope you can see what's coming next. And so indeed, we'll just use the same format. So we'll say that the localization function LXY is just the convolution of KX and KY. And LYX is the same thing, KY with KX. And those 2 will actually be the same function. And so we'll just talk about 3 functions here going forward. I do want to point out that we're not the first to think of using kernel convolution in this way. So there have been a couple papers where similar kernel convolution has been used to construct scale-dependent localization functions and localization functions for variable length fields. We do think that we're the first to do this to construct multivariate localization functions for strongly coupled data assimilation. And we also think we're the first to do this convolution with the same kernels that Gaspari and Cohn used for their most widely used localization function. And so just to show you what this cross-localization function will look like, here are the two on the diagonal. Here are the two localization functions, standard Gaspari and Cohn that we were seeing before. And then the off diagonal, we can see these two functions are actually the same, and this is the cross-localization function that we'll use. So right away, you might notice that this localization function is not, the cross-localization function is not 1 at distance 0, and that's you know, just a product of the convolution, and it's also turns out to be necessary for non-negative definite matrix. So we'll see that in other functions that we look at in the future. And so the questions that we asked were, can we construct a cross-localization function so that the whole localization matrix is non-negative definite? And we have done that. I didn't show a proof here, but I'm happy to talk about that in questions later if people want to go over that proof. But indeed, this formulation does ensure that the localization matrix is non-negative definite. And also, this function is compactly supported, so this cross-localization blocks are going to be sparse, just like we wanted, which is all well and good. And now we have this, you know, set of 3 functions that we're calling multivariate Gaspari and Cohn. We're calling this whole collection multivariate Gaspari and Cohn. But the real question is, you know, what's the performance like, right? And so we'll ask a couple different questions, but the first question that I want to start with is, how does this multivariate version of Gaspari and Cohn compare to just a simple univariate version? So by univariate, I mean, what if we use the same standard Gaspari and Cohn function for all components, and we just pick one length scale for all components? And so here you can see that we've picked the shorter length scale. This was experimentally determined to be the best univariate setup. So we want to compare our best multivariate versus our best univariate. And what we're going to use to compare these two different localization functions is just a bivariate Lorenz 96 model, which is a conceptual model of atmospheric processes. And so we have this Y process in black, which is a short process and can be thought of as rapidly varying small scale convective fluctuations. And then we also have this larger red process, which is referred to as X. And this can be thought of as smooth large scale waves. And so the governing equations are here. And I won't go too much into these, but there are some different parameters here, and we pick basically all the same as Lorenz did in his 1995 presentation 96 paper, except that we do vary the coupling strength H from what he chose. So I'll just go through our experimental design. We observe every Y variable and none of the X variables. And then we're going to look at the performance of the data assimilation in the X process. So we're really trying to isolate, you know, what's the impact of this cross-domain assimilation, and specifically what's the impact of these cross-localization functions. We are observing at every time step with an observation error variance of 0.005, which is about 5% of the climatological variance of the Y process. And then we use a coupling strength rather, H equals 2, which is double what Lorenz used. And that's just to increase the impact of these cross-domain covariances, so that we can actually see some impact from our cross-localization here. our data assimilation scheme is ENKF with perturbed observations. We're using adaptive inflation, and finally we're using 20 ensemble members, which is a relatively small ensemble size, and that's intentional because we want to see, we want to really see the impact of localization, and so we want to accentuate the spurious correlations, and we do that by keeping the ensemble size pretty small. So I'm showing here two histograms rather of RMSE for the X process. I'm showing univariate versus multivariate, and we can see that the multivariate histogram is shifted to the left, and so our performance is better with multivariate Gaspari-Cohn than with just the univariate, which is encouraging, at least to us. Hopefully this is another tool that we can have in our strongly coupled data assimilation toolbox. There is one final question that I want to address here, which is how does multivariate Gaspari-Cohn compare to other multivariate localization functions? So we'll compare this to 3 other multivariate localization functions. Bullen and Wallen is another one that's created through kernel convolution, and this is actually a second multivariate localization function that we introduce in this paper. However, it is based on some work done by Bullen and Wallen in their 2016 paper, where they develop spatially adaptive covariance models for non-stationary fields. ASCII and Wendland are not created through kernel convolution and are presented in the Daly et al. 2015 paper, also investigated in Rowe et al. 2015 for use as localization functions in data assimilation. And so I'll show you the same histograms that we saw before, and also just at the same time as we're looking at these 4 multivariate functions, we'll just go ahead and look at their univariate counterparts as well. And so for univariate, I'm using just this localization function with the smaller localization radius. And so here we go. And the first thing that we see is, Gaspari-Cohn, the multivariate is doing better than univariate. For Bullen and Wallen and ASCII, multivariate and univariate are doing about the same. And for Wendland, the multivariate is actually doing worse than the univariate. So I'll just break this down a little bit. The univariate histograms, maybe you can convince yourself, and it is actually true that they're all quite similar, which makes sense because all the univariate functions actually look pretty similar with such a small localization radius. And so what we're seeing is that not only is multivariate Gaspari-Cohn doing better than univariate Gaspari-Cohn, it's doing better than any of the other 7 localization functions that we are testing against.
Sorry, Zofia, I'm sorry to interrupt, but you only have 2 minutes left.
Okay, great, sounds good. So these insets are showing the cross-localization function that we use. And so the blue line is the univariate function and the red is the multivariate function. And so just briefly, I think what we're seeing is that for Gaspari-Cohn, we basically think that the shape of this cross-localization function is nice in a couple of different ways. And we sort of think that it's tall enough and wide enough. And I won't go into the details there, but there are more details in our paper if you'd like to look. And so some current work that we're working on is we're observing every X variable and none of the Y variables, then also observing every other Y variable with double the observation error, and also varying the coupling strength, all within the bivariate Lorenz 96 model. And then we're also working on implementing these localization functions in a coupled ocean atmosphere model. So we're using QGCM, which is a mid-latitude basin scale coupled ocean atmosphere model. And I'll end there. I have my email up on the screen. I'm happy to take questions now. And if you have further questions, I'm always happy to take them by email.
Thank you, Zofia, very much for this very interesting talk. You have a lot of questions, and I think it's more like a discussion going on the YOPED or Etherpad, but we are actually running out of time, so we'll skip the question for now, and then you can take a look at the YOPED or Etherpad and answer their questions. Thanks again, and we'll move on to our next talk.